introduction to discrete event systems. So I will define what discrete event systems are and how they fit to the system theory that you are familiar with from the previous courses during the bachelor study, and that is also or will be also elaborated in the course on linear systems this semester. So I started the recording, and I will, as I announced before, I will also I will use the notebook in OneNote to write the notes to the lecture. So there is no presentation here, and the notes will be written in the notebook. So we have what we are familiar with regarding the modeling of the systems. We have models of systems. Just let me check that it can be seen. Yes. Just let me know, please, if you can see the notebook and my writing there. Okay, good. Thank you. Yes. The lecture notes are visible in the notebook. So if you have a look at the notebook in Teams, then you can see my notes. Okay, the recording. Yeah. So I write it on the tablet, not on the computer, and I share it from. I share it from the computer. So this is something which I don't know how to do it. Okay.
Maybe somebody else can share their screen.
Okay, good. That's a good idea. So we have the models of systems, and what we are used to is that we have continuous variables which change their values together with time or as time evolves. Typically systems reacting to the outer world and so on. If we have a look at computer-based systems, they are typically representative of systems that use discrete variables. So such as counting parts, phone calls, execution of operations in manufacturing systems, so finishing the operations, customer arriving in a queue, and so on. So like counting task, and so on. Such processes are usually driven by events. Driven by events. So, for example, when we push a button, it starts, or it, yeah, okay, we can say that a reaction is executed as a result of a button being pushed, or a new part is inserted in a system. Another example, which also relates to computer-based systems, is communication protocol. Communication protocols. Typically, or we can say that we model the system in a way which I'm going to show right now. I have some problems with the picture. Okay, so the system is represented as inputs, as something which has inputs and outputs. This is clear, and the system can be represented with a model where there is an input vector dependent on time, output vector dependent on time, and there is some transfer function relating the input, the output to the input. So we have systems which are time varying and systems which are time invariant, and you just to summarize this time invariant system is a system which behaves in the same way, independent on the instance of time where the behavior happens. So we can say that if we have change of the output depending on the change of the input at some time instance t, and then at a certain time shifted by tau, so the system at time which is shifted by tau behaves in the same way as was the behavior at the time instance t. If the input is the same as it was before. We can describe the system in a, with a state space model where the internal states of the system are represented by a matrix or by some other way, especially relating to the discrete event systems, which will be mentioned later. And if we know the state at time t0, so it's time t0, then we can determine the output yt, where t is bigger than t0, based on the state and on the input. So if we consider the system model denoted here, we can describe its internal behavior, dynamics of the system, like function of the state of the inputs and of the time, where taking time into account means that it is time varying. If we do not consider, then we have time invariant. So this is a general definition of the system state and system dynamics. Of course, we in most cases, which is the discipline of system theory and of the system theory, we need to control the system in a defined way, typically in a closed loop, using a closed loop. And this is a general discipline, which can also be applied to the discrete event systems. So as I announced at the beginning that we will be dealing with supervisor design. So the term of supervisor relates to controlling or to closing control loop to the system, so that the supervisor in terms of the discrete event systems is the name for a controller, which relates to the system theory that you are familiar with. We can have an example of a tank. So let me get the picture here. So let's have a tank where we have the inlet pipe where the flow is denoted as lambda t, and the outlet pipe where the flow is denoted as mu t. And we need to define the state variable, which is denoted as xt and represents the level of the liquid, the level which is filled in the tank. There is also the maximum. There is also the maximum level which can be reached, denoted as K. So the K represents the constraint so that the water level, which is the state of the system, is constrained by K. So xt is the state variable. And the system dynamics can be simply represented as the difference between the inflow and the outflow. Lambda t minus mu t. And there are several possibilities which may happen, so that we can represent it as 0 if xt is 0 and the inflow is lower than the outflow, or if xt is k and the outflow is greater than the inflow, greater or equal. Otherwise, the dynamics is the difference between inflow and outflow. So if the system is not constrained by 0 or by k, then the dynamics is represented by the difference. We can have a look at so-called sample path, which represents the behavior of the system for various shapes of the inputs. So let's have a sample path like this. This picture represents various sample paths 1, 2, 3. So evolvement of the state variable over the time, depending on the evolvement of the input over the time. In this case, the sample path is continuous. It represents the continuous state space. Or we can choose another representation. Which is discrete. So for the continuous sample path, the state variable is any value in the interval between 0 and k. In the discrete case, the state variable is represented by integer values. Sorry, I actually it can be any value. Just I said it in a wrong way. So in both cases, this is not the representation of the discrete state space. Here we can see the description of what was denoted here. So this definition is represented by this figure, and this remark about the integer values relates to the discrete model, a discrete situation, which will be talked about later. Regarding this picture, we can describe the breakpoints of the graph. So let's take this example where we can have something like this. So for this state variable x1t, we can have lambda 1 which can have various values depending, but we also need to know what the outflow is. So let's take value of mu being 1, and then for this sample path, if we have the value of lambda, for example 3, then for time between between 0 and 1, the dynamics will be 2. So this is the slope of this. Of this path here. Then from time 1, we sorry, for time from 1 to 2, the lambda will be 3 as well, and but from this part we see that the state variable is not changing anymore, which means that the tank level is constrained by its upper limit, so that In this case is a 0 and the tank is overflowing. The tank is overflowing. If we take next part from 2 to 3, then the dynamics is -1, so that lambda will be 0, and from 3 to 4, or we can say that it continues further here, so it's not limited by 4, so we can say that t is greater than 3. The lambda is 0, so that the dynamics is 0 again. The second sample pass would be computed in a similar way. So here, with a continuous system, with continuous state variable, we can see that it's quite tricky to describe how the system variable is defined, because there are the changes of the system behavior are related to specific changes which are not continuous but represent from a, let's say, certain point of view, represent steps in the step changes or changes, abrupt changes in the variables. If we get back to this notion where the state variable is represented as integer values, or it can be represented as symbols, set of symbols, for example, on, off, then we talk about a discrete set that represents the state space. So this represents a discrete state space, and this represents continuous state space. So in this case, the state is a subset of R. In the second case, in the discrete state space, it is represented as a discrete set. We can have also hybrid models. Where some state variables are discrete and some are continuous. So we can have a look at another example. Which is a discrete state system where the state variable xt is the number of products in the warehouse. So it will be represented by integer numbers. Then we can have input, let's say U1, which is either 1 if a product arrives, at time t, and 0 otherwise. And the output would be equal to the number of products in the warehouse. So we can draw a sample path for such a system. Where the red circles represent the arrival and the green circle represent the departures. Whereas the departures can be represented as a second input variable where it is 1 when truck arrives, which means departure of the product, and 0 otherwise. So that we can describe the evolvement of the system dynamics at a certain point. So it seems that there is not the drawing. The drawing has not been copied. I will. Yeah. So we have the individual time instance and the circles, red circles and green circles represented arrivals and departures. And the system dynamics can be written in such a way that it is the previous value increased by 1 or decreased by 1. Otherwise, it will be 0. Sorry, it will be the same. So it is arrival, which means U1t is 1 and U2t is 0, and here we have departure, U1t is 0 and U2t is 1. And the last case is otherwise. Let's have a look at this notation. So typically this means change of state, but it relates to continuous time and also continuous change of the state variable. But this is not our case. We have step changes at the respective time instance. So we cannot use this notation, but let's define a notation t plus, which means just after time t. We can. So this is the sample path, and we had to define a new notation because of the discontinuities in the sample path, in the changes of the state variable. So this t plus means just after t. So it cannot be expressed by differential equations as in the case of continuous systems. We can also notice that during the time which is depicted on the sample path, there are only a few points when the events happen. So the events like truck arrival and product arrival, which means that in fact it doesn't make, or it's not so efficient to express the state space in terms of continuous, let's say, as if we were expressing the behavior of a continuous system, but we focus on the state changes. State changes. We may compare to discretized we may compare to a discretized system where we have sample path sampled at equidistant time instances having the same length, 3t, and so on. So if we apply a sample and hold circuitry, we will have such an involvement of the sample path. So this is discrete sample path, and this is continuous time sample path. So discrete time sample path. So we can see the difference between discrete state space and discrete discretized sample path with respect to discrete time instance. And thus we can also see that the events cause state transitions and that they may also occur instantaneously. So, which means two events may occur at the same time. And typically, in the case of the warehouse, we can define a set of events as a set having two elements, like product arrival, truck arrival, product, truck. Other examples of events may be operator presses a button, computer goes down, and so on. Which leads us to a distinction of, or to another way how the systems can be distinguished. Such a distinguishment is to time-driven systems, time-driven, and event-driven. In time-driven systems, which is an example of this sample path, which is sampled by equidistant equidistant samples. So it is an example of a time-driven system. So we have continuous variable which is discretized at equidistant time samples. So it can be a continuous state systems. And in the discretized time, the clock drives the sample path. In discrete state systems, we can also have time-driven behavior, which means that at every clock tick, an event is selected from the set of events. So an event is selected, can say executed with every clock tick. And this is called that we have a system which is synchronized by clock. It may happen that no event is selected if no event occurs. If we have a look at the sample path from the warehouse, so for example, the distance between T4 and T5 is longer than between T3 and T4. So if we take, for example, the distance between T3 and T4 as a sampling period, then we can see that if we add the sampling period to T4, then no event can be seen, no event occurred. So that there is a, yes, sure. Okay.
I have similar problem.
Me too.
Okay. Okay. So I see it in my tablet, but do not see it in the computer either. Okay. So I will try to find. It seems that there are some problems with the connection speed. So if the connection is slow, then also the update is slow. And I will put the notes on the channel and to Moodle, and hopefully you will be able to to match the sound with the notes later. So you can see the sample path from the warehouse. Can you?
Yes.
Okay, sure, good. So I was talking about the interval between T4 and T5, which is longer than the, let's say, virtual sampling period that, as I said, would be the interval between T3 and T4, which means that that at this moment we do not detect any event. No event detected. Or we can say that there is no event. So if we have a time-driven system with discrete states, it may happen that at the sampling intervals, no event occurs and no state change is performed. This situation is handled by event-driven systems, which means that the state change is performed at various time instance. Various lengths of the intervals. This can be understood as interrupts in computer systems. This leads us to characteristic properties of discrete event systems. So, the discrete event system is a discrete state event-driven system and its state evolution depends on the occurrence of the events over time. Depends on events occurring over time asynchronously. So this is contrary to the time-driven system where the clock ticks are occur at equidistant time intervals. So we can simplify the sample path of a discrete event system so if we draw okay, now it stopped also with me, so I have to restart the notebook. Okay. So if we draw the timeline, then we draw the time instance T1, T2, T3, T4, T5, and so on. And at each time instant, an event occurs. So we have E1, E2, E3, E5, sorry, E4, E5. Then we can write a timed sequence as a sequence of tuples represented by the event and the time instance. So it will be sequence of E1, T1, E2, T2, and so on up to E5, T5. And at each event, state change may be performed. So we start from an initial state, let's say S5, which is initial state, and then we have a state change to, let's say, S2, S4, no change state with E3, so we remained at S4. Then we have state change to S1, and so on, so that we can also write a sequence of states. So if we start from S5, then we go to S2, S4, and so on, and finish in S1. So if we know such a sequence, we can recover the system state at any point of time over the sequence. We can also predict the behavior of the system if we know the sequence of events. So we can match deterministically the state changes to the event changes. Of course, as I said, we need to know some. Then we have to know the initial state. The set of events is an alphabet. So that it leads us to talking about language, which is a set of all sequences. As a set of all sequences. If we have a look at the time sequence that I wrote, so E1, T1, E2, D2, and so on. So it is a time sequence. So there is a timed instance. There is a time instance assigned to each of the events. So we can talk about a timed language. Timed language. If we also associate some probability with the events, we can talk about stochastic timed language. And on the contrary to this, we can remove all the timing and probability information, and we get an untimed sequence. Or just logical behavior. So if we assign these three ways of describing discrete event systems to our course, so we will start with untimed sequence or logical behavior of the systems. Then we will move to a timed language as a second part, and as a third part to the stochastic timed language. So regarding the logical behavior, we are interested in ordering of the events, and no time behavior is considered. If we talk about timed language, then we are interested in event timing, and we can ask questions like if a task can be completed before a certain deadline, or how soon can a state be reached. So how soon can a task be executed? How long does it take before a task is executed? And such a modeling formalism allows us to assess performance of the system. So like throughput, response time, and so on. By considering the stochastic behavior, we also may include some events or actors that are not under our control. For example, behavior of an operator, or modeling the fact if a system goes down or if a system is broken, and so on. So this is what we will be dealing with in this course. And I think this is where we can finish today. And next time we will continue with formal description and modeling of automata, languages, and so on. I am sorry for the inconvenience and for the technical problems. I will try to think of another way how to do it till next time. So hopefully it will be better, and the recording will contain synchronized image and sound. I can see a hand of Mr. Papelham. Okay. Okay, so are there any questions? If not, then we will meet next week. I will put again the time into the calendar, and just to remind you, next week we are going to have 2 lectures, one at 14:30 and the second at 16:15, so that you can start working on the task after that, on the first task. So thank you for your attention, and see you next week.